Okay, hello everyone. This is Volts for February 7th, 2025. What's the deal with enhanced rock weathering to store CO2? I'm your host, David Roberts. If we want to restore a safe atmosphere, we will need not only to stop emitting carbon dioxide, but to start pulling it out of the atmosphere and permanently sequestering it. Lots of it. Billions of metric tons of it. There is broad and intensive work being done right now on various methods of carbon dioxide removal, most of which, like industrial direct air capture, seem dauntingly expensive and infrastructure intensive. One method that has attracted a great deal of attention and money lately is enhanced rock weathering, ERW. Truly one of the worst in a family of terrible acronyms. ERW, which at least in theory, could get started using existing infrastructure. ERW sets out to accelerate the natural process whereby carbon in the air bonds with silicates in rock to become bicarbonates, which eventually filter their way down into rivers and oceans, where they are stored for thousands of years. That's the theory anyway. This is a normal part of the terrestrial carbon cycle, but ERW turbocharges it by crushing up and exposing large volumes of basalt rock, mainly on agricultural land. Farmers already distribute crushed rock over their fields, so the infrastructure to do so is in place. They just need to use a different crushed rock. Is ERW the first carbon removal technology with a clear path to scale? Needless to say, there are all sorts of devils in the details. To dive in, I'm excited today to talk with Zeke Hausfather. Zeke is a climate scientist, modeler, and communicator, a longtime fave of the online climate world. But what's relevant here is that he also works for Frontier, a fund that is helping to scale up carbon dioxide removal and has a lot of money ready to go for ERW. So let's get nerdy with this. With no further ado, Zeke Hausfather, welcome to Volts at last. Finally, I've been wondering when you'd finally make it over here.
Thanks, David. Yeah, I've been a long-time listener, first-time guest. So,
first, I just want to say, am I right? I heard your colleague Jane on a different podcast talking about rocks, and she is, by her own acclamation, rock-pilled, has gotten very excited about this. Am I wrong in saying that this seems to have kind of elevated itself a little bit among the carbon dioxide removal choices as sort of the most promising short-term move here? Is that accurate?
I think it's definitely one of the more promising short-term options we have, both on a cost basis and also a time basis. It takes a long time to build a giant new industrial scale facility for something like direct air capture. Putting rocks on fields is low tech. And as you mentioned, farmers have been doing this forever with carbonates or limestone. The problem, of course, with carbonates, as the name implies, is they have carbon in them. And so really all we're talking about here is switching from carbonates to silicates, which don't, or, applying silicates on land that traditionally have not been limed.
Right. So what we have here is then, at least in theory, the prospect of sequestering pretty large volumes of carbon using infrastructure that is mostly already built. So this is a way you can get immediately started, which is, I think, unique among major CDR options.
It also is an approach that potentially has less objectionable aspects than some other ones.
Yes.
It's interesting. There's a lot of CDR approaches that involve adding alkalinity to natural systems. Ocean alkalinity enhancement is the most prominent one. We've talked about river alkalinity enhancement before.
Can we just pause there for the science illiterate among the Volts listenership, including its host? Can you just talk briefly about what we mean by adding alkalinity and why that matters, why it helps?
Sure. So in rocks like basalt or olivine are cations, particles like magnesium, calcium, a little bit of sodium. There's not that much in the rock. And these particles are very basic. So they neutralize acid and that neutralization of acid, if done to carbonic acid, which is, very prevalent in soil pore water because, rain comes down with a bunch of carbonic acid in it, forms bicarbonate minerals, which are durable. They get swept out to the ocean and stored for, tens to hundreds of thousands of years before eventually precipitating down as carbonates, which then get subducted, come out as volcanoes, and the cycle repeats. And so this is, as you mentioned in the intro, the biggest driver of the natural carbon cycle over geologic time. So every year, the world sequesters about a gigaton of CO2 from the atmosphere in the form of primarily silicate weathering.
And this is just an array of base materials absorbing the carbon out of carbonic acid and making it into rock, basically.
Yeah. As rivers run through their beds, they weather some of the, basaltic minerals or other mafic or ultramafic minerals. Those then form bicarbonate. And so that gigaton that's being removed every year from natural rock weathering is roughly balanced by about a gigaton of CO2 coming out of volcanoes every year. And so those two are in balance over, tens to hundreds of millions of years.
Right. So this process that we're talking about is underway all the time. It's natural. It's removing about a gigaton of CO2 a year. So the idea here is just to take this ongoing natural process and just boost it.
Yeah. So it's a big number globally because the globe is really big. But, a given chunk of rock is going to weather very, very slowly unless it's already in superfine form. And so the idea is to speed up this weathering process by ideally, initially at least, using waste fines, so leftovers from construction aggregates in basalt quarries.
Yeah, I want to get to the source of the rock, but just on the question of how to accelerate it, it's just as simple as increasing the surface area exposed to air and rain. Is that all there is to it?
So the conditions also matter a bit. The warmer and wetter it is, the faster the material weather, all things being equal. More acidic soils will tend to result in a bit faster weathering than more basic soils. And if the soil is too basic, you can actually get carbonate precipitation. So, it forms carbonates, which is not great. You ideally want it to form bicarbonates to get exported. It's one of the reasons that folks are targeting enhanced weathering projects in, fairly acidic soils like the eastern US, like Brazil, like India, areas where the level of acidity in the soils has actually become a problem and started hurting crop yields.
So there are geographic constraints in where this can be applied.
Yeah. You don't want it on soils that are too basic. You don't want it in a place that's really cold. Now, there might be some ways around that. For example, there's a number of folks looking at a material called wollastonite in Canada. Canada is cold, not that wet, but wollastonite is super, super reactive. There's just in the range of tens of millions of tons of it readily accessible, not, tens of billions of tons like we have for basalt.
Let's talk about where the rocks come from and what the rocks are. So what you want is rocks with lots of silicates in them, right? And those are mostly basaltic rocks, mostly volcanic.
Well, you want rock ultimately with lots of calcium and magnesium, but ideally you don't want fossil carbon in those rocks. And so limestone, for example, has a lot of calcium in it, but it also has carbon. Whereas silicates like basalt have a lot of calcium, but don't have the carbon. They have silica instead. And so the silica itself is not the active ingredient, so to speak.
Right.
It's the calcium, or in the case of olivine, the magnesium.
And so give us a sense then of are there any material constraints in our ability to find this kind of rock? Or like if we scaled this up, where would we be getting these rocks?
So basalt is more or less one of the most common substances on the planet. It comes out of volcanoes that strip the CO2 out of it. And so it can reabsorb that CO2 on the flip side when it weathers in the future. The challenge, though, is that you have to move a lot of material, and you ideally want to locate areas that have relatively acidic soils or could otherwise benefit from enhanced weathering that are within, say, 100 miles or so of a source of basalt. If you're starting to go longer and longer distances, you start getting a bigger and bigger hit, at least in today's world. Maybe in a future when we have completely electrified transportation, that's less of a burden, but it certainly adds to cost as well. So today we're primarily looking at, locations where there's basalt near farmland. There are some other materials like olivine.
And that's just a natural that just happens geologically in some places, not others.
Yeah. I mean, basalt is in deposits in certain regions and less common in other regions. Though, again, it's pretty common all around the world.
What about these waste rocks that you're talking about using? What are they from?
So when people quarry basalt today, it's primarily used for aggregates, for road construction, that sort of thing. And it turns out that you don't really want the rock dust in your roads. You want like small particles. And so today, when basalt is quarried, they produce a huge amount of byproduct dust. Somewhere around 15% of the rock is waste fines, as they call it. And they pile these up in giant mountains next to the quarry. And when the quarry closes, they bulldoze it in, fill it up, call it a day. But those fines are exactly what you want for enhanced rock weathering because they've already been ground up to, really fine conditions.
Oh, good point.
And at least in the US, most states require that basalt be washed before it's sold to reduce the risk of dust exposure in projects. And so because of that, you end up with really, really fine particles from that washing process that are, recovered and stacked.
So that waste rock then is when you find it ready to be distributed, there's no additional processing that needs to happen to it?
Not really, no. I mean, again, it depends a bit on how fine it is. And there's some quarries in some states that have finer fines than others. The bigger challenge is just there's going to be a limit to the amount of waste fines available. Today there's somewhere in the range of 10 or so million tons of waste fines produced per year in the US, which, is still a decent amount of CDR, but it's certainly not talking about the scale we're thinking about in the long term. There's another, maybe 50 or 100 million tons of fine piles that have accumulated from previous quarry activity. But eventually you're going to run out of that. And at that point, you're going to have to grind new rock that's quarried specifically for enhanced rock weathering. Now, that isn't necessarily as problematic as you think from a emissions perspective.
Wait, I want to pause on this point because I want to get a sense of scale here. So let's envision in the future a fully up and running global, enhanced rock weathering business. How big of a chunk could the call it 20 million pounds of basalt waste, how big of a chunk is that? I mean, is that 1%, 10%? How far can we get with the existing waste piles, I guess is what I'm trying to get at.
Well, we're talking tons per year, not pounds. But regardless, there's about 0.4 tons of carbon removal per ton of basalt when it fully weathers.
Mm-hmm.
And so let's say somewhere in the order of 5 or 6 million tons per year of carbon removal would be possible from existing streams of waste fines. Add in a fair bit more if you, mine these legacy piles that have just accumulated in the past. But we're not really talking about beyond the 10 million ton range available from fines in the US. Obviously other countries have fines as well. But if we're thinking about hundreds of millions or billions of tons of carbon removal per year from enhanced rock weathering, you quickly run out of these wastes and you have to do dedicated quarrying.
Got it. The reason I'm trying to clarify this is just that so this industry, if it really got up and running, could get a boost, a head start with existing waste rock, but eventually would have to transition to basically digging up and crushing rock on its own.
Yeah.
That would be part of the industry in the end. You're not going to ever get enough quarry mining to sustain what we need.
Yeah. And there already are some companies today that are doing dedicated production. Some projects in Brazil, for example, are using new rock. Projects using olivine, which is a much more material with a much higher CDR potential. So you get 1 ton of CDR per ton of olivine compared to 0.4 for basalt. That is purposefully quarried today for projects. So, a little bit of this is happening, even if most of the players today are starting at least with the waste fines if they can.
And if you dump a bunch of this waste rock on a field over and over again, year after year, are there no trace contaminants in there that might mess with your soil? Is this rock really clean in a way that's going to be okay fertilizing plants?
So you do have to be a little careful, right? You have to make sure you're characterizing what you're putting on the fields.
Right.
Most basalt deposits are pretty benign. There's not much contamination of things you don't want, but you'd still want to test it just in case. And at least with basalt, there's not really a huge worry about the accumulation of anything problematic at the rates we're talking about here. Olivine is potentially more of a challenge because it has high levels of nickel in it. It also has high levels of chromium, but it's not the chromium that we're worried about. It's chromium-3 rather than chromium-6, which is not bioavailable. But even then, you'd want to carefully monitor that.
Are people mining olivine for other reasons, or is it just a sequestration thing?
So there's a few other industrial uses of olivine. It's used in some steel-related processes, but global production of olivine is relatively small. There's huge reserves. There's hundreds of billions of tons of olivine accessible, but historically it's just been not a particularly valuable commodity. The one other challenge with olivine is, depending on the deposit, it could be co-located with asbestiform material, or asbestos as we call it. And so you want to make sure that the olivine you're getting doesn't come from deposits that have asbestos contamination because no one wants to put that on fields.
Right. And this is all of this care and consideration goes in on the front end. You're not going to crush up a bunch of rock and then do stuff to it to purify it. I'm guessing that would just add a bunch of cost.
Yeah, it's pretty impractical to strip out things. You want to test on the front end, make sure the deposits you're working with don't have any contamination that's problematic. And then once you're starting to deploy this on fields, you are sampling the soil every year and making sure there's not a buildup of nickel or anything else that would be problematic. The good thing is if there is, if you start seeing nickel levels that are higher than you want, you can always stop.
Right.
You're not going to end up in a situation where it's, you've contaminated the soil and it's too late because.
Right. It's a slow motion process.
And you're just not adding much rock, per unit of soil. You add a lot over the entire farm, but any given piece of soil gets a small amount each year.
One more question about constraints. So the amount of waste rock is somewhat of a constraint. You'll have to shift to quarrying its own rock. The geographic constraints we discussed, you need deposits of basaltic rock in proximity to acidic soil, basically.
Or other alkaline materials, olivine, wollastonite. There's folks looking at things like steel slag or coal ash, but those have their own issues.
Yeah, coal ash would be interesting. Anyway, you need a source of some material next to acidic soil. Is that a meaningful restraint, or are we going to be able to get all we want out of those areas?
So, this is by no means a silver bullet, right? Our best estimate is probably somewhere in the range of 1 to 2 gigatons per year potential of enhanced weathering globally, at scale. To put that in perspective, we're emitting 40 gigatons per year today. Most of our scenarios have somewhere in the range of 6 gigatons per year of negative emissions by mid-century to deal with, leftover emissions in the economy that we can't fully reduce.
So even best case scenario, this is a relatively small piece of the carbon dioxide removal puzzle.
Yeah, it's probably, if I had to guess, 10 to 20% of the solution by mid-century.
Do you think it will be the single biggest piece?
That's a tough question to answer. I think the other one that is competing for that prize in the near term is biomass-based carbon removal that has its own challenges around sustainable sourcing, making sure you're not, cutting down trees to stick carbon underground, that sort of thing. The other area we're seeing a lot of movement in the near term is on big biomass-based carbon removal projects, either things like biooil, like Charm Industrial is doing, biochar, waste injection of biological solids like Volted is doing, or the sort of big BECCS-style retrofits of bioenergy plants that we're seeing in Europe.
I just have such a thing about biomass. It's so messy and so tangled in so many different problems. I have a real aversion to it. So what about, you said alkalinity is sort of a family of solutions here. Talk us through a little bit about why you'd prefer to do this on agricultural land versus, my understanding, the two main alternatives are you spread it on the beach, which I guess gives you more confidence that it's going to end up in the ocean, or you just put it in the ocean directly. Why would you prefer one of those over the others?
So what you put in the ocean is going to differ a bit from what you can put in soils for a couple different reasons. One is that soils are an environment that's really good at dissolving rocks in a way that's not necessarily true for marine environments. If you put basalt in the ocean, it's going to sink to the bottom, get mixed in with the sediments, and never really dissolve. The ocean's just really bad at dissolving basalt. It's too basic. The chemistry is different. It doesn't really have the conditions good for that. Olivine could dissolve in the ocean, but even then, it's taken a lot longer than folks initially expected in some of the field trials folks have done around spreading olivine on beaches. And so there is some potential there, but it doesn't really fit well in today's markets because it's really hard to measure once you put stuff in the ocean.
We're going to get to that in a minute, that whole thicket.
For better or worse, when you put stuff in a field, it tends to stay there until it dissolves, which is not true for other environments, which makes the tracking somewhat easier, though there are other challenges.
I see. So you think doing it on land is going to win in the end, or there will be some of each?
I think there'll be some of each, and I think it might be different materials. Like I think basalt is pretty firmly only going to be used in farmland, pasture land, maybe forest land. I think that if you're looking at rivers, there's been actually some interesting work being done there with traditional calcium carbonate. Even though it has some carbon in it, it still ends up being net CDR.
Huh.
It's not as efficient as silicates would be, but it dissolves a lot faster in fresh water. And then in the oceans, there's a lot of interest in what we call ocean liming. So that would be taking limestone, heating it up in an electric calciner, stripping the CO2 out of it to produce calcium oxide, sequestering that CO2 underground, and then putting that calcium oxide in the ocean. But that ends up being a lot more complicated because you're sort of doing a traditional CCS technology on top of then distributing this calcium oxide in the ocean.
I know.
The last approach that we're seeing is electrochemical approaches for ocean alkalinity enhancement. And there you're essentially taking seawater and using electrodialysis or similar approaches to split the seawater into an acid and a base. And you're taking that acid and disposing of it, question mark exactly how, and putting the base back in the ocean to enhance the alkalinity. And so that doesn't require any material. You're just splitting apart seawater with energy, but it requires a lot of energy, unlike the other approaches.
Interesting. So this is just yet another area where if you could reach that Valhalla of basically trivially cheap renewable energy, this is one of the things you could do with all that surplus renewable energy is speed up carbon dioxide removal.
Yeah, there's sort of two backstop technologies in the carbon dioxide removal world that could scale almost infinitely given enough cheap, clean energy. And those are direct air capture and ocean alkalinity enhancement, particularly the electrochemical types. But we're still pretty far from that world today, and it's pretty hard to justify projects that use a huge amount of clean energy that might otherwise contribute to grid decarbonization in the near term.
So back to this, you're spreading it on the soil, on agricultural soil, and the idea here is that it forms bicarbonates, and then the bicarbonates end up through the natural cycle, filtering down into rivers and then ending up in the ocean. And it is them ending up in the ocean that vouchsafes their permanent storage, basically. So one of the questions that came up when I was talking about this online earlier is that there seems to be some new research that shows that they're staying in place in the subsoil, basically, which risks, I guess, them losing their carbon again if they encounter the wrong kind of material. So I'm just curious about recent research. How confident are we that these things are actually making it to the ocean, which is kind of the whole premise?
So we're quite confident that they'll eventually make their way to the ocean. There is the potential, particularly in some types of soils, that you could have lags in the soil itself, or cation exchange site lags, as we call them. This is an area of very active research. There's been one paper that got a lot of criticism from one side, but support from another. But even that paper suggested that it really is going to be regionally dependent in sort of like sandy soils like in the southeast, or soils in Brazil that have strong fracture flow patterns where you have very rapid drainage. It's probably less of an issue. And somewhere like the Midwest, where you have a lot of water retention in soils, it's probably more of an issue. And so even, to the extent that this is a problem, and I think it is one that we need to take seriously, even if it doesn't affect the ultimate potential of enhanced rock weathering, it is going to be very regionally dependent. And it's something that folks, both academic researchers and companies, are starting to directly measure in deployments today, taking deep soil cores, down to 80 centimeters to track what's happening, not just at the surface, but in the deep soil.
Right. So just explain briefly, what's the danger here? What are we worried might happen instead of them going to the ocean?
Yeah. So in general, we're worried about anything that might cause either a delay in the effective carbon removal or a reversal of the carbon removal. Delays can be things like the cations, the calcium and magnesium, get stuck on soil exchange sites and don't sort of get out of equilibrium with the atmosphere for a couple of years, which then delays when the effective CDR happens. The other things we worry about is, it's possible if you add too much alkalinity to soils, or you're adding it to sort of basic soils, soils that are not acidic, that some of the bicarbonate can precipitate as carbonate. So essentially you lose half the CO2 you're storing, and that would make it half as effective. Now, that doesn't seem to be a big risk in most of the places we're targeting for deployments today. But if you tried to do enhanced weathering in, say, the Western US, you'd quickly run into problems with carbonate precipitation because the soils are more basic.
Right. But this is something you could track with testing. You could know if this is happening.
Well, if it's happening in the shallow parts of the soil, it's pretty easy to measure. If it's happening deeper in the soils, it becomes more difficult to measure. But it is something that we nominally can test for. And then the final area of leakage that we're worried about, the final main one, I should say, is what happens once the bicarbonate leaves the fields. And so there you could, drain into an acidic lake, for example, which would cause it to be re-released. You could end up, encountering acidic water in waterways in a different method, though, we do sort of track pH of rivers, so this should be something that at least is reasonably easy to assess. And then I think the biggest loss that we see in modeling, at least, is what happens when it reaches the ocean. And there, it turns out that fresh water, for various reasons, is better at absorbing CO2 by adding alkalinity than saltwater is. And so saltwater is about 15% less effective at absorbing CO2.
Oh, that's kind of a bummer, isn't it? If we have such big plans for storing CO2 in the ocean.
Yeah, but I mean, those numbers are sort of baked in, right?
Yeah.
But you do end up losing somewhere in the range of probably 10 to 15% of the carbon you capture in the rivers and sort of the coastal areas when it equilibrates with the ocean. And so those are all accounted for in projects today, at least as best we can.
Well, this sounds to me, let's go ahead and wrestle with the MRV then. This sounds like a nightmare to track. Like if there are things that can go wrong in the field and then deep in the field and then in the river and then in the ocean, and what you're interested in is how much of those bicarbonates made it to the ocean and got to the bottom and were safely sequestered. A, how on earth do you measure it and track it at all? But B, with such a complicated process, how do you get a shared measuring system upon which you can build actual markets?
Yeah. So one of the developments that increased confidence in enhanced weathering as a pathway and led to folks, starting companies and actually trying to do commercial projects with it is dramatic improvements in the way we can measure the dissolution of the material. So it used to be that folks suggested, I'm going to spread this rock in the field and then claim a carbon credit for it. And, obviously, if you're doing it on the wrong field or you're spreading like millimeter-sized chunks of rock instead of micrometer, it might not dissolve for 50 years, and it's not actually doing that much. And so what we've been able to do in recent years is fine-tune the measurements of the rock dissolution using mass spectrometry measurements. So essentially, what scientists can do is sample the soil in discrete locations before the deployment of the rock, immediately after the deployment of the rock, and then on an ongoing basis, either every 6 months or every year. And you can measure for the same location how much of the material is still there. But what you can also do, and this is particularly clever, is you can use stable tracers in the material to determine how much rock was applied in the first place. So for example, basalt has a decent amount of titanium in it. Not enough to cause any problems to the soil, but titanium is a super, super stable material. Once it gets into the soil, it doesn't wash out. And so if you know the ratio of titanium to calcium and magnesium in the soils, that actually tells you, both before and after the deployment, how much of the rock was applied to that spot and what percent has weathered based on how that ratio has changed. If you've lost half of the calcium and magnesium, but the titanium hasn't changed at all, you've weathered 50% of the material.
So that will tell you how much of the material has dissolved.
Yeah. So that's step one. That's when we can say there is, potential CDR has occurred. The rock has dissolved, it's released the alkalinity that should be interacting with carbonic acid in the soils and forming bicarbonate. Then we have to do deeper cores and water-based measurements to actually track where the cations are flowing through the soils. And here, it's a little harder. You're not going to do it like every acre like you would for the soil measurements. You're probably going to set up... Just
to be clear, just to back up for 1 second, the soil measurements, these are a human being tromping out into the field and doing something physical, right? This is a manual... It's
a manual process. It's building off, a huge existing industry for agronomic measurements and soil sampling that exists in places like the US. So it isn't a new thing. A lot of farmers get their soil sampled pretty regularly. This is just a bit more intensive than you'd normally do. And instead of just tracking soil organic carbon and a few other things in the soils, you're actually running them through a mass spec machine and doing an isotopic analysis or a elemental analysis of composition. So it definitely is a bit more expensive on that front. And actually today, MRV is a big part of the cost of enhanced weathering projects. A lot of projects we're seeing are spending $100 a ton of CO2 just on MRV today. But the idea there is that by collecting all this data at a very high granularity and high spatial resolution, we can then hopefully develop models that mean that, we're always going to have to do some measurements, but maybe if we have good enough geochemical models, we'll have to do fewer measurements in the future. And so a lot of what early buyers like Frontier are trying to do right now is effectively buy down the cost of the pathway by collecting the types of data we need at large scales to reduce these uncertainties.
And part of what we're doing right now is figuring out how much measurement we need.
Exactly. And making sure we're measuring all the right things.
Right.
I think that's the second challenge. Making sure we're doing enough deep soil measurements, we're doing enough fluid measurements. There's also some interesting potential as we start scaling enhanced weathering deployments to do measurements at a watershed basis.
Like I can imagine measurements in the field of a variety of kinds. And I can imagine measuring like, okay, we dumped X amount on here and then, Y amount is gone. So that means X, certain amount is free in the soil now. But how do you measure that it got into a river and then subsequently that it got into the ocean?
Yeah. So deeper soil measurements can show how the cations are flowing through the soils in fields themselves. But once you get to the rivers, you can also measure these concentrations of dissolved inorganic carbon, of free cations in the water. Now, the challenge with that historically has been that depending on the watershed, there could be a lot of different fields draining into that one river. And if you're doing like a single field in this entire watershed, you run into a huge signal to noise problem. But once we start seeing much larger scale deployments, like we're seeing in Brazil right now, for example, on thousands or tens of thousands of acres, then it becomes a lot easier to see a signal in river data as well as in the fields. The oceans are always going to be a bit of a modeling world just because, the further downstream you go, the more dilute everything gets. But thankfully, we are actually pretty good at modeling ocean chemistry and, carbonate chemistry in the ocean in particular. And so there might be a couple percent uncertainties, beyond our best estimate.
But help me with this, Zeke, because the ocean's real big. You put a little bit of base material in it, from one field, it's like a 1 to kajillion ratio. Are you really able to detect that level of change?
Well, again, you're modeling what's happening in the ocean. You're not measuring it directly, but it's also important to emphasize that the actual carbon removal, the capturing of the CO2 in the formation of bicarbonate is happening in the soils. You're not actually relying on the oceans to do anything except for store the bicarbonate. And oceans store an immense amount of bicarbonate. There's something in the range of, I forget if it's 20 or 60,000 gigatons of bicarbonate in the ocean. And so changing that a little bit isn't going to affect ocean chemistry significantly. And so as long as you're accounting for the dynamics of carbonate chemistry equilibration when it reaches saltwater and reaches the ocean, once it's there, it should be very stable. And there's not much uncertainty on that front.
So you helped write 4 Frontier guidelines for companies doing this on how they should measure and verify what is sort of good practice versus bad practice. Having gone through that exercise, are you now personally comfortable that we are able to measure this in a way that you feel confident about, that you would feel confident building a multi-billion-dollar, market on top of? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts, people using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. Are you now personally comfortable that we are able to measure this in a way that you feel confident about, that you would feel confident building a multi-billion-dollar, market on top of?
So I think the challenge with enhanced weathering is that we have to make sure people are doing it right. The barrier to entry is so low to spread rocks on a field.
Yes,
that,
it's very true.
Anyone can kind of do it and make claims. But the actual doing the science right behind it, having a lab that can do, hundreds of thousands of mass spec measurements, that can, do all the sampling management and track the data over time, like that's a much higher bar. And so what we put together in these guidelines was essentially a guidance for buyers who are thinking about enhanced rock weathering, like what to insist to make sure that it is doing it right, at least as right as we can today. Now, to your question of, am I confident in this? I think that it's always going to have more uncertainty than something like direct air capture. But at the same time, it has a lot more co-benefits. We haven't even talked about yield effects of VH management.
I just worry because this is something that, comes up a lot in discussions of carbon credits and the exchange of carbon credits, which is just that the market actor has an incentive to want to maximize their apparent carbon removal, and buyers just want the cheapest carbon removal they can find. So they're not super incentivized to scrutinize this. Sort of like nobody involved has a direct, incentive to make sure things are done. So it's all, you're putting all that weight on the regulators. You need really good, really alert regulators in a market like this, because there's just incentive to fudge around every corner, it seems like to me. Do you not worry about that?
I mean, that's certainly the story of what we sort of call the legacy carbon offset market writ large. Avoided deforestation credits, renewable energy credits under the Clean Development Mechanism. That was additionality, baseline manipulation. There's no end to shenanigans.
Yes, there. All that stuff. Does all that stuff not transfer right over to here? I mean, these things are being sold on carbon credit markets already, aren't they? I mean,
yeah. So I think there is a real worry that the market will move that way. I think right now we're sort of in a weird situation where there are a pretty small number of buyers. Like for enhanced rock weathering, at least, it's Frontier, Google, who's a Frontier member but has done some of their own stuff, and Microsoft. And all three of us are primarily concerned about getting this right and scaling these technologies rather than maximizing the amount of tons we can claim. That said, that's going to change.
But this is true of any small early market, right? I mean, this is unusual.
And so I think now is the time to put in these safeguards, to have external standards organizations, to have registries that are putting science first. And in the case of enhanced rock weathering, we actually help support a big community effort run by a nonprofit called Cascade, that brought together 49 different academic scientists, as well as various other folks in the community, and spent a year putting together a Foundations of Enhanced Rock Weathering document that sort of lays out the best practices for how to address each of these uncertainties. And we've seen the registries, the isometrics, the Puros, the folks who put their stamp on these credits, increasingly align with that effort. So I think there is a real need for external scientific bodies like what Cascade did to create standards for the field. I think there is a need for standards organizations that are not just the buyers and the suppliers. And to be honest, the registries themselves, depending on how they're set up, might not have the purest of incentives.
Yeah.
And so what we've been trying to do is not just, prove this out in the field, but also build all the supporting infrastructure on the science side to make sure, it's done right going forward. Because there is a real risk that someone does this badly, either creates contamination of soils by adding materials they shouldn't, or makes sweeping claims that can't be backed up by the actual measurements and creates a black eye for the field.
Right, or we just spend millions of dollars for nothing.
Yeah. I mean, we know this works on a macro scale, right? I think the uncertainties are primarily around timing and the magnitude of some of the leakages. I would be hard-pressed to see a world where there's more than 30% of the carbon that's initially captured lost before it's in durable storage. But that's still a pretty big number, right? Our best estimate is close to 15% now.
Tell me if this is crazy. This just seems like one of those things to me that's like, on the one hand, we know it's good, and we know that doing a bunch of it would be helpful. But on the other hand, it's just devilishly difficult to precisely quantify, exactly. Mm-hmm. So I just wonder, is quantification and credits and trading and buying of credits the right way to do this? Is there not some other way we could just sort of incentivize, do as much of this as possible? You know what I mean? And not pretend to be able to count the angels on the head of a pin. I don't even know what that would.
I mean, I feel like you're channeling my friend Jane Flegel, who this is one of her big arguments. I think there's some truth in that, right? I actually don't particularly like making offsetting claims with carbon removal, be it tree planting, enhanced rock weathering, or direct air capture. I think it would be a better world if we were doing this because it's the right thing to do, not because we're pushing around some number in a spreadsheet to counterbalance our emissions.
Right, and a big thing that the public, it's like waste removal. It's something that the public should pay for.
Yeah. At the same time, there's not really any other game in town right now except for private, voluntary carbon markets. Now, I don't think anyone thinks that's the long-term solution. Corporations doing things out of the goodness of their heart isn't going to solve our problems.
I have questions about this. Well, let's use this then to pivot, because one of the things that's intriguing about enhanced rock weathering, and one of the reasons I've paid attention to it when I mostly just screen out CDR talk for now, is that there are reasons to do it aside from carbon storage, and therefore there might be reasons that people would pay to have it done other than carbon storage. right? Because carbon storage doesn't help anyone, right? It helps everyone, but it doesn't help anyone in particular. It's not really something that is of value to people beyond the sort of PR of appearing to be doing good things, right? Which, and I'm skeptical how far that's going to take us. But putting this stuff on soil does positive things to the soil that are a potential source of value. So talk us through that just a little bit.
Yeah. And just to cover my bases in my previous argument, because I don't want to leave it on a statement that the volunteer carbon market is completely useless. Like, I think how we see it is we're using this decade to create a bridge toward a world of compliance markets, of government procurement, of mechanisms that actually scale this, that are not just corporations acting under the goodness of their heart. So things we do right now should be aimed toward that, not just maximizing tons on paper. But on the co-benefits front, there's a few different co-benefits that are important to mention here. One is that we've seen increased crop yields associated with enhanced rock weathering deployments. This is particularly true if you're deploying in a region that hasn't historically been limed. So where you haven't added limestone, you're not replacing it, you're just doing something new.
And what's the mechanism? Why would that happen?
So there's two mechanisms where enhanced rock weathering can benefit crop yields. The primary one, that's the most straightforward and most well understood, is simply managing soil pH. If soils get too acidic, plants get less good at taking up nutrients, fertilizer is less effective, you have to add more of it, and your yields are lower. And today, farmers add enough limestone to their fields to get to the point at which the cost of adding more limestone is more than the yield benefit they get.
Right. So this is why there's this giant industry in place already to spread crushed limestone on fields. It is to bring down the acidity of the soil.
Exactly. But most farmers don't add as much lime as they should if they really wanted to maximize yields, because at some point it just gets too expensive or too operationally complex to add more.
Oh, the limestone gets expensive.
Yeah, or the yield benefits per unit of additional limestone decline after a point. Yeah.
Do we have any sense of how much this kind of rock would cost relative to limestone?
So it's generally going to be a bit more expensive than limestone, simply because you need more material to have the same pH benefits for soils. At the same time, if you're effectively subsidizing farmers deploying this based on the carbon benefits, you could more effectively manage soil pH. So instead of stopping at the point at which you hit diminishing returns, you could actually add as much alkalinity as you can to maximize crop yields, because the carbon removal scales pretty linearly, even if the soil benefits start decreasing after a certain point.
And the carbon removal will pay for it.
Yeah. There's also a lot of parts of the world, like smallholder farmers in Mexico, like rice paddies in India, where, there just hasn't been historical pH control because there's not the availability of limestone, or it's too expensive for farmers to do. And there, we see really big benefits of this. There's a company called Mati in India that's shown very large increases in rice yields. There's a company called Flux in Kenya that's seen similar findings on smallholder farms there. So you really get the biggest bang for the buck if you're taking an agricultural system that hasn't done any mineral amendments, any rock amendments, and putting in silicates.
That's a pretty big deal. That's a pretty big benefit.
Yeah. And so there's a lot of potential interest in what are the development dividends of this in the global south. So you could sort of get 2 for 1, right? Help farmers increase their yields and sequester carbon. But the other way that you could potentially get higher yields from basalt compared to limestone is because basalt has a bunch of micronutrients in it that limestone doesn't. Limestone is pretty pure. There's just calcium carbonate. And so those various nutrients like manganese, zinc, other things the silicate itself actually can also help with crop growth. And so we've even in side-by-side trials where you put the same sort of liming strength equivalency of limestone and basalt on side-by-side fields, we're starting to see bigger yields from basalt, though we still need more data there. A lot of these field trials are still in their early years.
Interesting. So this is a source of value to farmers. So how is this going to be integrated in the sort of market for this stuff? Like, how do you envision it working? Like, I'm a company, I go to a farmer and I say, hey, you're currently spreading limestone on your fields. I can supply you with a different kind of rock to spread on your fields, and you'll get boosted output from it, and we'll pay you to do it. Like, what is the business model here?
Yeah, so we've seen a few different ones. Some of the early companies are just paying farmers to spread the rock, period. They're not charging them anything. So they both save on not having to pay for limestone if they previously did that, and they get the rock to spread for free. And the revenue from the sale of carbon credits covers that. There's other folks who are looking more at models where you essentially charge the farmer a small amount, but you're still subsidizing a lot of the cost through carbon markets. And the reason for that is again, as I mentioned earlier, you simply need more material in most cases for silicates than you would carbonates. Olivine is the one exception there, but olivine is also harder to get to a place. It's less ubiquitous than limestone. And so for example, Ion, which is a company that's doing olivine-based enhanced rock weathering, is barging their olivine from Norway, which sounds crazy, but it turns out...
Holy moly.
Oh, no. It turns out barging is remarkably efficient. Like the carbon impact of barging is incredibly small compared to the distance traveled.
Oh, interesting.
But it still adds to the cost, primarily. And so that affects it as well. And so it's hard to see a world where farmers are going to do this without some sort of incentive for the carbon benefit.
Yeah. That's what I was going to try to get at. Like, do we envision this? Like, could we envision this being the one kind of carbon dioxide removal that doesn't need a constant flow of public funds? Do you know what I mean? Could it ever be self-sustaining just based on these co-benefits? Or you think it's just like going to take the price down a little bit?
It's going to be a tough sell in most places to apply silicates compared to carbonates without some sort of incentive based on the climate benefits. Now, where I could see this happening is twofold. One is the existing voluntary carbon market that we see right now, which for all its warts and flaws is putting money toward this. The other that's potentially more interesting long run is this idea of supply chain insetting. So there's a lot of companies that have huge agricultural supply chains making food products. And agriculture is one of these fiendishly hard to decarbonize parts of the economy. Yep. And so this is one of the few ways that agriculture can durably store carbon as part of the agricultural process. Soil carbon, organic carbon is the other, but that's its own can of worms. No pun intended.
So could this show up in the Farm Bill then? Like, is there interest in this outside of sort of carbon nerd circles?
There is. So there has been some push to create a conservation standard as part of the Farm Bill that would give a subsidy for the application of silicates for soil pH control, similar to how there's a conservation practice for things like biochar right now. That's, a relatively small amount of money, but every little bit helps. I think the other thing that folks have been looking into is that there's some ways to sort of create a pay-for-practice system at a bigger scale. So essentially, pay folks to spread silicates at larger scales on farms through Farm Bill type incentives, or carbonates for that matter. Liming is not great, but it turns out that, particularly if you keep adding limestone beyond a certain point, it does become CDR, albeit half as effective.
So all this lime spreading that's happening right now is in some marginal way a version of CDR.
It is. It's just not very good CDR. And there's sort of an ongoing debate about how much of the benefit is counterbalanced by interactions with other acids in the soils, which is also a risk for silicates, but less so because you don't have the carbon penalty, right? But in an ideal world, if all of it dissolved and all of it formed bicarbonate and all of it went to the ocean, limestone would be about 40% as effective as basalt or olivine.
Interesting. And so just like on the front end, the supply of waste rock is like enough to get started, but not enough to sustain this at scale. We did end up having to dig up rock and crush it. Similarly, how big of a offtake is agricultural land? Like, is that going to be able to absorb all the rock we can dig up, or are we going to eventually run out of that too and have to find different places to spread this?
So our best estimates, and I think I mentioned this earlier, is that global farmland and pasture land in the places that have the right conditions that are, close enough to a source of rock could probably scale to between 1 and 2 billion tons or gigatons per year. Once you want to go beyond that, you're going to have to look into different approaches. And that could be superficial mineralization of these materials. You create a big pile of more reactive stuff and let it carbonate. You could potentially try to get it to dissolve in waters, but that is just harder with silicates, like putting it in rivers or beaches. There's other ways that folks are looking into doing this beyond just agricultural fields, but it seems at least today that this stuff dissolves by far the easiest in agricultural settings.
Right. So just like waste rock and agriculture are the starting gun, kind of like the ways to get this up and rolling.
Exactly. And agriculture might be the ending gun too, depending on, how much we end up needing to scale this.
Right. How well it works. I'm trying to get a sense of like how much infrastructure would be required once this is scaled up and how much energy is required, maybe relative to like other CDR proposals. I mean, you need transportation of the rock, the spreading of the rock. I assume like that's in place. So, I mean, it just seems like to get started here, there's not a huge infrastructure barrier. Is that accurate?
Yeah. So today, particularly if you're working with waste fines, all you really need to do is to find farmers who are willing to do it with you and find some trucks that can carry it from the quarry to the field and then use existing spreaders. You do need bigger spreaders in some cases. So folks have used manure spreaders and others just because you're dealing out more material than you would with liming. But you could also use a smaller spreader and run it more times. You just have a slightly bigger hit in terms of the emissions if it's a gas-powered vehicle. But overall, when folks have looked at life cycle assessment studies of this, it's somewhere around, only about a 5% hit to CDR over the life cycle associated with transportation and spreading.
All of that accumulates to 5%.
If you're using waste fines as a starting point. If you're doing dedicated quarrying, that could be higher. It's going to depend on a lot of factors like what is powering your grinder. Is it electricity? Is it what's the grid in the region? But that said, we're pretty good at crushing rock efficiently, at least down to the 100 micrometer scale that we're talking about here. If you want to get it really, really fine, then it gets exponentially more difficult. But for the size of particles we're looking at for commercial deployments today that'll primarily dissolve in the first 5 years, you could probably do it for, maybe another 3 to 5% hit on life cycle.
I don't know. It's just like when I think about mining, digging up millions of tons of rock, that just sounds like a big deal to me. This is better thought of as quarrying than mining. And the reason is that most of these basalt formations that we'd be using are very close to the surface. So you're not creating giant, deep mines to get this material out. You're just sort of scraping it off the surface. There still obviously is impacts of that, right? Quarries displace, forest land or farmlands. They create, potential impacts in the community and potential jobs in the community. There's trade-offs here, but a single quarry can produce a huge amount of material from a CDR standpoint. So, even if the scale to a gigaton scale globally, we'd be doing a 40% or so increase in the current scale of global aggregate production, somewhere in that range. Very interesting. So let's talk about Frontier and what it's doing and what you sort of envision the sequence of events here, the sequence of political events and policy events. So Frontier was started because we need a lot of CDR. Governments are not doing what they need to be doing. So the idea here is you're collecting private money. You're offering what are called advanced market commitments, which just says, if you can sequester the carbon, we will pay for it. So just talk a little bit about how that works in the context of this, what that means.
Yeah, so if we go back in time a few years to say 2019, when Stripe Climate, which then sort of developed into Frontier, originally started, there was a huge amount of talk about carbon removal and pretty much nothing happening in the real world, And so Stripe Climate was, the first customer of Climeworks, of Charm Industrial, of all these initial startups in the early days of this market. But they quickly ran into a problem where there was no real buyer for expensive, durable carbon removal, in part because there are existing carbon markets, but they were paying, I don't know, I think the average price now is $4 a ton.
Yeah.
Which if you are paying $4 a ton.
These are optimistically $100, $150 a ton, right?
Yeah. And if you look at things like direct air capture, you're probably upwards of $500 a ton today. So certainly some of the technologies are expensive. But the point is that these can get cheaper, and the only way to make them cheaper is to actually do them in the real world and learn how they work. And so the idea with Frontier was less about maximizing the amount of tons we're removing and more about being catalytic on the technology side to essentially use this decade to figure out what works and what can scale to sort of maximize shots on goal. And that's one of the reasons that we try so many different approaches in ocean alkalinity enhancement, enhanced rock weathering, direct air capture, bio-oil injection, BECCS. There's dozens of different types of CDR approaches.
So do you have concrete advanced market commitments, AMCs? Do you have them out on paper to all those technologies at this point?
So there are two different types of projects Frontier does. The first are small-scale pre-purchases, which are really almost grants. We don't count any carbon from them for companies. But the idea there is it's a lab-scale prototype with some professors with a good idea want to build their first project. And so those are $500,000 initial sort of grants with a potential $1 million re-up if they show progress. So that's one side of the equation. That's trying to find all the crazy new ideas that might not work, but at least we want to, try them. And that's sort of where we started. But the other side that's becoming much more of the focus now that some of these pathways are maturing are large offtake agreements. These are usually somewhere in the range of $20 to $50 million agreements that are pay on delivery. So essentially we say, we will buy this many tons over this period from this facility or building, but we will only pay once those tons have been removed from the atmosphere and verified.
Yeah, this is just crucial to emphasize. This is not, we're going to give you money and we hope you go do this. It's, if you can sequester the carbon and demonstrate that you did it, then we pay.
Yeah, we'll give you a purchase order. But the important thing there is that that company can then take that purchase order to the bank and say, hey, look, we have this $50 million deal with these very reputable companies. Can you lend us money to build this first of a kind plant? It's still challenging for them. Like, they'd prefer to get the money up front, to be honest.
I'm sure they would.
But we also want to hedge our bets here a little bit. And so, again, the idea with spending the $1 billion and change that we're going to hopefully be spending by 2030 is to really catalyze as many different areas as possible. And at this point, we've done offtakes in enhanced rock weathering. We've done offtakes in direct air capture. We've done offtakes in multiple different types of biomass approaches. We've done offtakes for river alkalinity enhancement, wastewater system alkalinity enhancement. Haven't done anything directly in the ocean yet, but
this is slightly off our topic, but I'm just curious, so I have to ask. So, like, as you say, there was a bunch of talk years ago, but nobody really knew. It was mostly talk. Nobody's really doing anything. So nobody really knew what kinds of things would work. There's a lot of big ideas floating around. Now that you've had, 5 years of real practical experience funding and building these things, are there sort of macro conclusions that have emerged about sort of like what are the promising areas and what aren't? Like, have we learned enough to foreclose any routes or elevate any? Like, what are the kind of the big things we've learned?
There are some examples of pathways that just haven't really panned out. Macroalgae sinking is one that got a huge amount of attention a few years back.
People love that. So that's not paying off. Huh?
No, it turns out it's really hard to actually do in practice and really hard to track what's happening. And one of the bigger companies that raised a lot of money in that space ended up shutting down last year. And so, that's an example of an area that, we've probably pivoted a little away from. We can't fully preclude a possibility that something would work there. It's just been a lot harder than expected. And in general, we've gained a recognition for how hard it is to build things in the real world.
Yes.
And one of the sort of corollaries of that is that there's something to be said for low-tech approaches. One of the reasons why pumping poop underground or doing enhanced rock weathering or adding lime to rivers, it's pretty easy to do. You don't need many miracles, as we say. Whereas stuff like direct air capture has huge potential down the road, but you need both huge amounts of cheap, clean energy, and you need a lot of technological developments.
Yeah.
At the same time, you could make the argument that you might get more learnings from building a DAC plant than spreading rocks in a field. But, spreading rocks in a field, we're still taking a huge amount of measurements, doing a lot of science in that too. So I think it's too early to preclude particular pathways here, but we've definitely seen some fall in cost faster than others. And some like direct air capture that are still promising in the long run, are probably going to be a bit more expensive in the near term than we originally thought.
Right. And so through this process is what sort of enhanced rock weathering kind of rose to the surface as A, low tech, B, able to get started using existing infrastructure, and C, has some co-benefits that could ease its passage into the real world. I mean, is that accurate? That's why this one has sort of like gained a little prominence.
Yeah, I'd add one more to that, which is that people don't mind doing things to farms that they would mind in other contexts. So there's been a huge amount of difficulty in getting ocean alkalinity enhancement projects up and running. Part of that is some mess around the London Protocol and dumping and, legacy of the Russ George guy who tried to dump iron filings up the coast of Galapagos and rogue geoengineering experiments.
Right, I forgot about that.
So that's cast a whole mess over the field. But even beyond that, there's been a lot of community opposition to putting, to be honest, what are pretty benign chemicals like, magnesium hydroxide into waste pipes because it's putting chemicals in the ocean, even if...
But we've sort of made peace with science and farming together, right?
Exactly. We already put all kinds of stuff on farmlands. And so even though it all ends up in the ocean at the end of the day, it's much more palatable for environmental groups and for others to do interventions in farming systems than in natural systems like the ocean.
So the big arguments in favor of enhanced rock weathering, sounds to me then, are political economy arguments. They're practical.
I mean, it's also relatively low cost compared to a lot of other pathways and fast to deploy. You're not spending, 3 to 5 years building a giant facility. You can put rocks in the field next year.
And if we were hoping for substantial cost declines, where would those come from? I mean, like the advantage of the infrastructure already existing is that you can just start using it. But the disadvantage is that to the extent you can squeeze costs out of that infrastructure, a lot of them have already been squeezed out. So maybe there's not a lot more to squeeze out. Like, do you envision this getting much cheaper over time?
So I think compared to where we are today, which is the very, very early days, it can get a lot cheaper. We're seeing somewhere in the range of $300 a ton, for most projects today, some a bit cheaper, some a bit more expensive.
There's just a bunch of tests going on, right? Like, this is not happening. Everything that's happening around this is a test at present, right?
Yeah. I mean, some of them are being done by commercial companies, but they are very much, being research driven at this point. We're not seeing scaling to like millions of acres or hectares with projects operating today. And so, I think costs can come down in a few ways. One is we can get the MRV cheaper. We can have models that we trust and not being paying $100 a ton to do huge amounts of mass spectrometry measurements of soil cores. Another is that we can just get economies of scale in terms of efficiency and logistics. A big part of that is getting more favorable agreements for the feedstock with quarries. If you're a bigger customer, you can get down prices a lot. Part of it is, getting more farms that are closer to quarries enrolled, reducing transportation costs through larger loads or bigger, deployments. There's a lot of different ways that, some of these costs can come down. And so we think that ultimately the range of costs we're looking at on a dollar per ton of carbon basis down the road is probably somewhere in the range of $80 to $150 a ton of CO2, which is still expensive, but for permanent carbon removal, stuff that takes carbon out of the atmosphere for, tens to hundreds of thousands of years or more, that's among the cheapest that we have today.
I was going to say that's relatively cheap in the family of permanent sequestration methods.
Yeah. It's not going to be cheaper than planting trees, but it's also a different thing.
It's still quite aspirational.
Yeah. But even today, $300 a ton is on the cheaper end of.
Oh, good God.
But again, we're 5 years in, right? Everything is a first of a kind project today.
Yeah. The whole reason Frontier exists is that national governments were not doing what they need to be doing. And given recent developments in national governments, it doesn't seem like we're entering a period where there's lots of good policy that's going to happen. But nonetheless, in the spirit of hope and optimism, if the U.S. government got religion on this, what kind of policy would you like to see?
So I think you raise a bigger challenge here, which is something that keeps me up at night a little bit, working in at least part in the CDR world, is that CDR only really makes sense if we solve the other parts of decarbonization. Like if we're emitting 40 gigatons a year in 50 years,
yes.
CDR is going to be setting money on fire.
And I know you know that, and I know that. I hope everybody else knows that, because I get real worried that there is a class of people who would love to see this as an excuse to keep going on fossil fuels. Yeah. I know that those people exist. I
mean, if you're spending even $100 a ton, not to mention $300 or $500 a ton to remove carbon from the atmosphere after you put it up there, that's a lot more expensive than, 80 to 90% of the emission reductions we can do globally today.
Yes, it would be the most expensive way to go about it.
This idea that people are going to just do a ton of CDR down the road to clean up our mess doesn't pass the smell test. And I think that in that sense, the high cost is a bit of a feature, not a bug. Like I worry a lot more about the moral hazard issue with the $4 a ton offset credits on the voluntary market today than I do, $500 a ton DAC credits. Nevertheless, I think it's important to be clear how we talk about this. But yeah, to your question, I think that this is only going to scale if governments take climate more seriously broadly, and if governments take CDR more seriously as we start getting closer to meeting our climate goals. And those two sort of go hand in hand. We started seeing during the Biden administration some important steps in the Department of Energy around procuring CDR. They had a procurement prize. It wasn't a huge amount of money. I think it was like $50 million.
Right. So one thing government could do is just exactly what you're doing, these advanced market commitments.
No, we'd love to see a frontier for governments. Yeah. We shouldn't spend too much money on that. Like if we spend 1% on CDR of what we're spending on mitigation globally, I think that would be fine today. It's probably going to be 10% by mid-century or more as we start getting closer to net zero and don't have to do as much mitigation. But we're also spending, $2 trillion a year on clean energy globally. And so 1% of that is still not chump change.
Right. So advanced market commitments, do you think that's the main thing? Just because they're technology neutral, they get everybody moving, towards a common goal. Is that it? Or do you want DOE doing direct research in CDR?
Yeah, I think we need a few different ways that the government can be involved here. One is on standard setting. As you mentioned earlier, There is a real need for strong guardrails to avoid repeating the mistakes of the legacy carbon market here. And to the extent that the government can play a role there, I think it's a really important one. At the same time, we need to be careful because, as the legacy of corn ethanol teaches us, government itself is subject to some regulatory capture on the science side. So it's not a perfect thing, but it certainly can play an important role on the standard setting side. I think direct procurement is a useful function. And I think there's also just a lot of basic science that still needs to be done. NOAA can develop better sensors for ocean pH that can help, validate ocean alkalinity enhancement experiments. There's a lot more interesting science that is being done, particularly in some of the more emergent CDR pathways that I think the government has a strong role in supporting. So I think, AMC type approaches, direct procurement, standard setting, and research are all areas that I think are important. We will see where that goes in the new administration.
Yeah, I was going to say, it kind of feels like you're on your own for the next 4 years. Do you have any reason to believe otherwise? What is your sense of the bipartisan-ness of this whole area?
I think CDR, for some weird reason, code's a bit more bipartisan than other things. It's similar to nuclear in some ways in that regard.
Yes.
And I think we need to be a little careful if we embrace that to make sure that the arguments being made for CDR are accurate and not treating it as a get out of jail free card for actually getting rid of fossil fuels.
I worry that that's precisely why it's a little bit more bipartisan. It's because there's that hovering in the background. Well, Zeke, this is absolutely fascinating, as I suspected it would be. Thank you so much for walking us through this. And thank you, to all you folks at Frontier for getting going on this, because nobody else would.
Thanks. And again, we want to be humble and recognize that, CDR is 10% of the solution to climate change. But 10% of a problem as big as climate change is something that deserves having people work on it.
Absolutely. Absolutely. Well said. Thanks, Zeke.
Take care.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.